In this video, we're going to talk about elastic collisions, and we will also talk about impulse. So we're going to start first with the elastic collisions, and just want to do a quick review of momentum. At the time of recording this, this is coming back from winter break, and so if we remember, when two objects collide and there are no net external forces acting on the system, then we have the conservation of linear momentum. And so under that stipulation, um, if there are no net external forces acting on the system, then we can say that the linear momentum is conserved. And this is our relationship. Momentum, the initial momentum of object one and the initial momentum of object two will equal, let me write without talking, two, E2, will equal the final momentum of object one added with the final momentum of object two. And so if that's true, we can use this relationship. This works for all collisions. Today, we're going to come back to this. We'll talk about elastic collisions. Now, as a review, we have elastic collisions and inelastic collisions. When two objects collide and then they separate after their collision, if the initial kinetic energy of those objects is equal to the final kinetic energy of those objects, in other words, kinetic energy is conserved, we call that an elastic collision. If the kinetic energy is not conserved, we call that inelastic. Okay. So we're going to write down an equation here in just a moment for this one here. But first, we're going to get started on the problem. So let's come down and do an example here. Let's move this up here. Yeah, about right here. So I've already drawn the picture. You have two objects that are going to collide. 3 kilogram object moving to the right at 6 meters per second. 2 kilogram object moving to the left at 4 meters per second. And this time we're going to say they collide, but it is an elastic collision. In other words, there's no kinetic energy lost in that collision. So the total kinetic energy before will be equal to the total kinetic energy after the collision. And if that's true, yeah, it's gonna be a silent collision because when sound is produced in a collision, that means there's energy lost in the form of sound. And in this problem, we want to figure out I'm gonna relabel this. What is the final velocity of the first object and what is the final velocity of the second object? So let's get started on this. We're going to use the conservation of momentum, linear momentum. And I realize if I talk while I write this, I make mistakes on it, so I'm going to be quiet here. Let's double check this is correct. M1v1i plus M2v2i, M1v1f equals M2v2f, plus M2. Okay, looks good. The mass of object one is 3. The velocity of object one is a positive 6 because it is moving to the right. Mass of the second object is 2, and it is moving to the left at 4. That means -4 because we have to take account of that direction. So mass 1 is 3. We do not know V1F, big question mark there, and then we'll put in mass 2. We do not know V2F, and we don't need parentheses here, although you can leave it, it's fine. Cool, so 3 times 6, 18. 2 times -4 is -8. Which comes out to 10 equals 3v1f plus 2v2f. Excuse me. So One equation, two unknowns. We actually have seen this before many times. The only way you can solve something like this is if you have another equation. And what you do is you set up that other equation in such a way that we can substitute it into this one and solve for these velocities in this case. So we need another relationship here. Because we know that this is an elastic collision, we've started this problem saying that it is an elastic collision. Then we can use our equation for elastic only, which is V1I minus V2I equals V2F minus V1F. Double check, V1I minus V2I equals V2F minus V1F. Yes, this looks good. I think at the end of this video, I'm going to show how to derive this equation. It's an elastic collision. So this relationship is true. Remember that the kinetic energy is conserved. I will check, did I write that down right? Yes. And so we can combine our conservation of linear momentum, we can combine this statement about the kinetic energies being equal before and after the collision. If you combine these equations, we can come up with this relationship here. So at the end of this video, I think I'll show that derivation. Okay, now I'm going to skip some space because clearly we're stuck here. We're going to have to use this other relationship. So I'm going to go down here, start it here. Make sure you copy down the subscripts right. So V1I minus V2I, and we know those. This is, whoops, this is V1I, that's V2I. So this will be 6 minus -4 equals V2F minus V1F, which we don't know and we are stuck once again. 6 plus 4 is 10. Okay, let's not get too fancy here. We're going to substitute one of these. We're going to substitute an expression here into this equation. Best way is let's just make this negative V1F positive. So in other words, we'll add it to this side. And so we will substitute this expression here for V2F over here. So we'll continue. Let me do this in another color. V1F to 10 plus V1F. We can distribute the 2. Something like this. Now we only have one variable here, one term, one variable, V1F and V1F, so we can combine those. This is 10 equals 5 V1F plus 20. Just move this down here. We'll continue. Subtract 20 from both sides. That will be -10 equals 5 V1F, which is -10 divided by 5, which is -2. Now, really important for today's lesson, always show your answer as a magnitude and direction. And so we're going to write this as 2 meters per second. The negative means left in this context. Box in our answer. Always show an answer with units. In this case, show the direction and show what that is equal to. This is equal to V1F. So I'm just going to trace that over here. It's 2 meters per second to the left. So after the collision, this 3 kilogram ball will be moving to the left. Let's figure out what V2F is. And so we can just take this number And we can bring it up into this relationship here. Just this way. And so we have 10 plus V1F. Now we have V1F. And so my question to you real quickly here is, do we put positive 2 or do we put negative 2 into this equation? And of course, the answer is negative 2. And so this comes out to 8. But let's show that with units and a direction and show what that is equal to. 8 meters per second to the right, so I'm going to trace that on here. There we go. So you can do this again and use this equation only during an elastic collision if you know it's elastic. Cool. I think that's it for this one. I will just show, though, the meaning of this equation, which I think is really cool. There is a meaning behind this equation. V1I minus V2I. Well, V1I is 6, positive 6, and V2I is a negative 4, and that is 10. And these are velocities, and so that's 10 meters per second. And so what does that actually mean? Um, what does 10 meters per second mean? When this ball is moving this way and this ball is moving this way, what is moving at 10 meters per second? And it's not any one individual ball, but it is the rate of approach. It's how fast they are approaching each other. There we go. The rate of approach. Right? So this one's moving at 6 meters per second this way, and this one's moving at 4 meters per second. They are getting closer, closing the gap at 10 meters every second. Cool. Over here, we have 8 minus a negative 2, which is also 10 meters per second. And so what does that mean here? Well, this one is moving to the right at 8. This one is moving to the left at 2. And so the gap between them, the space between them, is increasing at a rate of 10 meters per second. This is the rate, whoops, of separation. Is this term over here. Cool. That's the meaning of that equation. Today, we're also talking about impulse. So this is, I'm not going to say it's completely unrelated. It's related in some ways, but yeah, it's a new topic. So impulse. I'm going to write down what the equation is for impulse first. We'll define these real quick, and then I'm going to explain what they mean. So this topic is called impulse. So of course, that's what we mean by J. In physics, we try to use the letter of the word as the variable notation, but well, not in this case. Impulse is capital J. And we'll say, what will we say? We'll say that J is the impulse delivered to the object, to a object. F average is just the average force applied to the object. You all know that force is in newtons. We'll talk about the units of this here in just a moment. And delta t, of course, this is the time interval over which the force or the average force is applied. The course is in seconds units. So, mathematically speaking, the impulse is equal to the average force times the time. And so if the units for force is in newtons and the units for time is in seconds, then the units for impulse is newtons seconds or newtons times seconds. Let's talk about what an impulse actually is now. And what I think about personally, what I think about when I think about impulses is actually about sports. Typically, most sports involve some ball of some kind, soccer. And let's just use the idea of a soccer ball, maybe a golf ball. And if you're kicking a soccer ball, you are applying a force to it with your foot, and it's typically not a constant force. As you come into contact with the soccer ball, your force will begin to increase. And as you are kicking it away, but it's still in contact with your foot, maybe the force is decreasing. The force that you apply is less as it's moving, as it's already starting to move away from you until loses contact with your foot. So the force is not constant. We'll say there's an average force that you have delivered that you have exerted on the ball, and you'll do so over a really small amount of time, right? Think about how much time it takes for you to kick a soccer ball. I mean, it's less than a second typically. So a very small amount of time, but it's still some interval. And so in physics, we say that you have delivered an impulse to the soccer ball. You can think about any sport. Also, a golf ball, is a good example. Um, so that's impulse. Um, yeah, not much to say else about this, at least for the moment. There's one more relationship, the impulse momentum relationship, and we'll call this impulse momentum theorem. If you apply, or I should say the net impulse delivered to an object will equal the change in the momentum of the object. Remember, that's a lowercase p. Now, we're not going to actually use the equation like this. We still won't use this one that I'm going to write here, but we'll need this. Change of momentum means mv final, your final momentum minus your initial momentum of some object. But the real form that we will use for this equation is we're going to factor out m from these terms. We'll say m on the outside of vf minus vi. And this is what we'll use. The net impulse is equal to m times vf minus vi. And by the way, um, impulse is vector. Force, you guys know, is vector. And yeah, so vector here, and then of course these are vectors, except mass, except time. And that just means that when you get an answer for these, you got to include direction. We'll change it. So let's talk real quickly about a soccer ball. You kick a soccer ball, you apply a force over a really small amount of time on the soccer ball, you give it an impulse. That impulse delivered to the soccer ball will equal its change in momentum. So the soccer ball is just on the ground sitting somewhere. The initial velocity is zero. So in this case, this term would be zero. And so your impulse would equal the final momentum of that soccer ball. Of course, the object might be moving initially, and we can just do the math there to figure that out. And let's just jump right into an example, I think. So the equations that we need are, yeah, that one, and we'll need this one a lot as well. So keep those. Excuse me. Let's jump right into an example. We have a ball that's moving with a velocity of 18 meters per second to the right. It's going to come into contact with the wall and bounce back off, but this time with a velocity of 15 meters per second to the left. The mass of the ball is zero point 0.6 kilograms. The time in which it is in contact with the wall, or the wall is putting a force on the ball, is zero point zero 0.05 seconds. Really small amount of time. Okay, what is J? What is the impulse delivered to the ball? And what is the average force? And of course, we have two questions, we have two equations. So yeah, on the homework, you'll use one and then you'll use the other. So let's do part A. Which equation makes the most sense to use to solve for J? Because both of these equations have J. Let's look at what we have. We have the mass, we have initial velocity, final velocity, and we have time. So yeah, just look at your equations, what you have here. We're going to use the second. Net impulse is mvf minus vi. And so we'll put zero point 0.6. The final velocity is negative 15. Whoops, why am I closing that? Minus the initial velocity, which is 18. So it's zero point 0.6 times negative 33, and then times zero point 0.6. Of course, I don't have a calculator next to me. You should see for yourself that this is negative 19.8. This is a vector, and so this is 19.8. The units for impulse are newtons, seconds. The negative means left. You guys see it. Okay. Um, let's just do part B over here. What is the average force exerted on the ball? Yeah, we'll use the other one. J is equal to F average times delta. Okay, we're going to put in J. We know J. We know impulse. So we put in 19.8 or negative 19.8. And of course, the answer is negative 19.8. Delta T 0.05. And we'll just divide these. We get negative 396 is equal to the average force, which of course means that the average force delivered is 396 newtons to the left. Good enough. Okay, let's talk about that force being to the left. When the ball goes and hits the wall, the ball puts a force on the wall, but the wall is putting on the ball a leftward force of 396 newtons, average force, I should say, of 396 newtons to the left on the ball. So that's the meaning of the left on for the force. And coincidentally, or not a coincidence, which means that the impulse delivered to the ball is also to the left. Cool. I think that's it. So clearly, whenever you're substituting numbers in here, if it was moving to the left, you've got to make sure you put negative back into that equation. All right. Cool. That's one example. You'll have some problems like that on the homework. And I'm just flying through the examples. Feel free to pause, whatever you need to do. Let's take a look at another problem here. There may be one, I think there's one, maybe two, but I think for sure one of these on the homework. And let's say a ball is falling and it's going to hit the floor. At the moment it hits the floor, moving down, it has a velocity of 12 meters per second downward. When it leaves the floor, and by the way, the floor will put a force on the ball over a time of 0.2 seconds. And when it leaves the floor, it will leave with a velocity of 9 meters per second upward. What is the impulse delivered to the ball? And B, what is the average net force? And C, what is the average force exerted by the ground on the ball? So you look at your equations, you look at what information you have available to you. We don't have average force, and so we must use the net impulse is equal to mvf minus vi. So we will say mass is 0.6, final velocity. And so we need to assign direction to this. And in the old days, which is, very recent, upward is positive. So we'll say that the final velocity is positive 9 meters per second, minus the initial velocity, which is 12 downward. We can say that's a negative 12. Mm. I like parentheses. What can I say? 0.6, and we'll say 9 plus 12, which is 21. And so it's 0.6 times 21. The net impulse is 12.6 Newton seconds. Positive, so we'll say this context is upward. Cool. Let's do part B. What is the average net force on the ball? Okay, so I'm going to use the other equation. J equals F average times delta T. Excuse me. Now, we want to know what is the net force on the ball. Because this is the net impulse, our answer from this will also be a net force, although again, it's an average net force. Average net force. It's kind of a so we just have to solve this equation. In other words, 12.6 equals average. This is the net force, the net average force times delta t 0.2. 0, technically, and then we'll just divide these. 12.6 over 0.2, 10, so positive, so move the decimal. Anyway, you should get 62 newtons. 63. 63 newtons. Positive, so it is upward. See if we can make a nice rectangle here. Yeah, close enough. 63 newtons upward. It's the average, but also the net. Yeah, it's also the net. This is the net force. You might be wondering, why do I keep making the distinction that it's the net force? Okay, which has to do with part C, but let's start with a free body diagram. When the ball is in contact with the ground, it has two forces on it, mg and Fn, right? So it's a normal force from the ground onto the ball, but it also has mg. Now we just calculated that it has a net force, so I can't hide that from you anymore. So there is a net force. So one of these forces must be greater. And you can ask yourself, in which way is the ball accelerating? Now, when a ball is in free fall, the acceleration is downward, but it's in contact with the floor at that moment, so it's not in free fall at that moment. And so there's not a downward acceleration. But look at the way that the velocity is changing. The velocity has gone from a negative, a downward velocity to an upward velocity. So that should make you realize that the net force is an upward force. And so Fn must be greater than mg. So that's why I'm making the distinction. The net force is equal to 63 newtons, but that's neither of these forces by themselves. It's both of them. So for part C, what is the average force exerted by the ground? In other words, what is Fn? The net force on the ball is simply Fn minus mg. We talked about that before. Two opposing forces, you add them together with the sign, and you get the net force out of it. We're going to subtract these, Fn minus mg. And we know the net force is 63 newtons. Don't know Fn. Mg is 0.6 times 10, which is 6. And so this is 63 plus 6. This is 69 newtons. The picture gives it away, but of course it's upward. Positive is the force exerted by the ground on the... Okay, you guys can see that. This is Fn. It's not working. Not important, but anyway, there we go. Oh, I think you have one. I don't know. I think you have one. I can look at it here. You can expect one of those on the homework. Cool. One last little thing here. On the homework, yeah, if you get a graph of force versus time, so that means force applied to an object over time. And it doesn't matter. Let's say it looks something like this. You're applying a little bit of force, and then as time goes on, it increases, but then it'll decrease. So on a graph of force versus time, let's say that the impulse is equal to the area. And by area, I mean this area under the graph, right? Let's do it like that. Impulse is equal to area. Cool. I think that's it. Of course, on your homework, the lines are straight, so that's easy to calculate, the area underneath that line. Okay. How much time is this video? I'm not sure, but I did say we would derive that equation, whoops, which is here. So can I steal these? Because I am going to need some more space. than what is available here. Oh, just a quick reminder, on your assignment, make sure that, for things that have direction, make sure you're writing the direction right, left, up or down, whatever. Cool. Let's derive this relationship. Be the last thing that we do here. So here's what we will do. Let's start with the conservation of linear momentum equation. I'm going to get all the m1s on one side and all the m2s on the other side. This is m1 v1i. I am subtracting m1 v1f from both sides. And we're going to get rid of this here in a second, so I'm not writing it. This is m2 v2f. Getting this one to that side, I'm going to subtract m2 v2i. To v2i. Just double checking I wrote that down right. Okay. I'm going to factor out the common variable here, which is m1. We're left with v1i minus v1f. We're going to do the same thing with m2. We'll factor out an m2 from these terms. This is v2f minus v2i left over. And we're going to leave that alone for just a minute. Over here, this is, again, only for elastic collisions, and so this statement holds. The kinetic energy combined and before the collision is equal to the kinetic energy after the collision. Every term has a 2 underneath, so we'll multiply both sides by 2. Do it like that, which cancels out all the 2's. This is m1 v1i squared plus m2 v2i squared equals m1 v1f squared plus m2 v2f squared. Well, let's do the same thing we did earlier. Let's get all the m1s on one side and all the m2s on the other side. This is m1 v1i squared minus this term, m1 v1f squared. We're going to get rid of this here in just a minute. This is m2 v2f squared minus m2 v2i squared. We'll do the same thing. Factor out m. This is v1i squared, v1f squared. We're going to do the same thing here. Factor out an m2. This is v2f squared minus v2i squared. By the way, do you ever need to show me any of this? Probably not. But if you're curious as to where that equation came from, it's kind of how we do it. My phone is ringing. So that's way over here. Okay. What we're going to do next is use something called the difference of squares. And so let's do that real quick. What is the difference of squares? It looks something like this. A squared minus b squared. There's a relationship here. It equals a minus b times a plus b. And you can use the FOIL method, I think that's what it's called, to work backwards and show yourself that you multiply these two together, you will get this, okay? And look at what we have here. We have a squared minus b squared, and we also have something similar, a squared minus b squared here, different a, different b. And so this is m1. Now what would this look like? This is v1i minus v1f times v1i plus v1f. Right, so we've turned this into these two. You can do the same thing over here. This is v2f minus v2i times v2f plus v2i. Cool. I'm just double checking to make sure I copied everything down right. Cool. And like we did today, and like we've done many times, when we have two equations, we're going to substitute one into the other. And look at this. Isn't that the same thing? And so we can substitute this right in there. We're going to replace that. So let's do that. This is M2 V2F minus V2I. Now that's, we're trading this, right? We traded that for this, but we got to keep this one. Was left over. M2. I'm just copying this down from what we had before. And you will notice that M2 V2F minus V2I is the same on both sides. And we're going to just divide that from both sides. It's not good algebra, but I'm just going to cancel those there. It's the same on both sides. So we are left with V1I plus V1F equals V2F plus V2I. Let's get all the I's on one side and let's get all the F's on the other side. So this is V1I minus V2I equals V2F minus V1F, which is our elastic equation, which again is the rate of approach, and this side is the rate of separation. Anyway, that's it. I'm going to end this video now.